Piezoresistive pressure transducers from Freescale. Welcome to this training module on Freescale's pressure sensor products. The intent of this training module is to provide the basic knowledge of pressure sensors and Freescale's featured products and their applications. In fluid systems, pressure and pressure measurements are extremely complex. A fluid can either be a gas or a liquid. Fluid and liquid are not synonymous. Fluid pressures can be defined as the measure of force per unit area exerted by a fluid, acting perpendicular to any surface it contacts. Pressure can be expressed in many different units, including in terms of height of a column of liquid. Pressure measurements can be divided into three different categories: absolute pressure, gauge pressure, and differential pressure. The absolute pressure is the difference between the pressure at a given point in a fluid and the absolute zero of pressure, or a perfect vacuum. Gauge pressure is the measurement of the difference between the absolute pressure and the local atmospheric pressure. Local atmospheric pressure can vary depending on ambient temperature, altitude, and local weather conditions. Differential pressure is simply the measurement of one unknown pressure with a reference to another unknown pressure. The pressure measured in the difference between the two unknown pressures. This type of pressure measurement is commonly used to measure the pressure drop in a fluid system. There are two types of fluid systems: static systems and dynamic systems. As the names imply, a static system is one in which the fluid is at rest, and a dynamic system is one in which the fluid is moving. In the static pressure system, a uniform static fluid is continuously distributed, with the pressure varying only in the vertical distance. The pressure is the same at all points along the horizontal plane in the fluid and is independent of the shape of the container. The pressure increases with depth and in the fluid and acts equally in all directions. Dynamic pressure systems are more complex than static systems and can be more difficult to measure. In a dynamic system, pressure typically is defined using three different terms. The first pressure we can measure is static pressure. This pressure is the same as the static pressure that is measured in a static system. The second type of pressure is what is referred to as dynamic pressure. This pressure term is associated with the velocity or flow of the fluid. The third pressure is total pressure and is simply the static pressure plus the dynamic pressure. The essence of piezoresistive pressure sensors is the Wheatstone bridge. Bridge resistors RP1, RP2, RV1, and RV2 are arranged on a thin silicon diaphragm such that when pressure is applied, RP1 and RP2 increase in value while RV1 and RV2 decrease a similar amount. Pressure on the diaphragm, therefore, unbalances the bridge and produces a differential output signal. One of the fundamental properties of this structure is the differential output voltage is directly proportional to the bias voltage, B+. This characteristic implies that the accuracy of the pressure measurement depends directly on the tolerance of the bias supply. Unlike the conventional pressure sensors, which utilize 4 closely matched resistors in a distributed Wheatstone bridge configuration, Freescale's pressure sensor is designed utilizing a monolithic silicon piezoresistor, which generates a changing output voltage with variations in applied pressure. The resistive element, which constitutes a strain gauge, is ion implanted on a thin silicon diaphragm. Applying pressure to the diaphragm results in a resistance change in the strain gauge, which in turn causes a change in the output voltage in direct proportion to the applied pressure. To make the designer's job even easier, Freescale's integrated devices carry sensor technology one step further. In addition to the on-chip temperature compensation and calibration offered currently on the 2000 series, amplifier signal conditioning has been integrated on-chip in the 4000, 5000, and 6000 series to allow interface directly to any microcontroller with an onboard analog-to-digital converter. The signal conditioning is accomplished by means of a 4-stage amplification network, incorporating linear bipolar processing, thin film metallization techniques, and interactive laser trimming to provide the state-of-the-art in sensor technology. Freescale pressure sensors combine advanced piezoresistive sensor architecture with integrated circuit technology to offer a wide range of pressure sensing devices for automotive, medical, consumer, and industrial applications. Here lists the design advantages and considerations to select different integration level sensors for different applications. Here lists the key features and typical applications for Freescale's MPXH series sensors. Here lists the key features and typical applications for Freescale's MPXV and MPXA series sensors. The integrated pressure sensors, IPS, have trimmed outputs, built-in temperature compensation, and an amplified single-ended output, which make them compatible with analog-to-digital converters on low-cost microcontrollers. With the higher resolution A to Ds, the noise that is inherent to piezoresistive bridges becomes a design consideration. The two dominant types of noise in piezoresistive integrated pressure sensors are shot noise, that's white noise, and 1/F, which is also called flicker noise. Shot noise is the result of non-uniform flow of carriers across a junction and is independent of temperature. The second, 1/F, results from crystal defects and also due to wafer processing. Noise can also come from external circuits in a sensor system. Power supply, grounding, and printed circuit board layout is important and needs special consideration. For mitigating the effects of this sensor noise, two general approaches are effective: low-pass filtering with hardware and low-pass filtering with software. When filtering with hardware, a low-pass RC filter with a cutoff frequency of approximately 650 Hz is recommended. The simplest interface is achieved with an integrated sensor and a microcontroller that has an on-chip analog-to-digital converter. The figure shows an LCD pressure gauge that is made with an MPX 5100 integrated sensor and an MC68 HC05 microcontroller. Although the total schematic is reasonably complicated, the interface between the sensor and the microcontroller is a single wire. The MPX 5100 has an internal amplifier that outputs 0.5 to 4.5 volt signal that inputs directly to an analog-to-digital port, PD5, on the HC08. Auto zero is a compensation technique based on sampling the offset of the sensor at reference pressure. Atmospheric pressure is zero reference for a gauge measurement, in order to correct the sensor output for long-term offset drift or variation. Sources of offset errors are due to device-to-device offset variation, trim errors, mechanical stresses, mounting stresses, shifts due to temperature and aging. Performing auto zero will greatly reduce these errors. This technique can easily be implemented when an integrated pressure sensor is interfaced to an analog-to-digital converter and a microcontroller. In order to use this technique, a zero pressure reference condition must be known to exist in the system. Here describes the auto zero algorithm.